let's move to the next talk by Kazuya Mameda. So Kazuya, could you please share your screen?
Yes. Yes. Can you see it?
Yes, I can see it.
Okay.
And yeah, please, he will talk about the rotational effect versus finite-sized effect on phase transition. Okay, please.
Okay, first of all, thank you for organizer, and thank you for inviting me into this good workshop. So today I would like to talk about the rotational effect and the finite-size effect in the rotating matter. And this is based on the collaboration with these two papers. And Kenji and Shugan is here. Okay, let us start. So in our universe, there are many examples of the rotating relativistic systems, such as a binary star merger and a black hole, neutron star. So on top of them, even on the Earth, we can create such a rotating system, namely in non-central heavy ion collision, total angular momentum transfer to the total angular momentum of ion transfer to that of hot QCD matter, and then large vorticity can be generated in the experiment. So indeed, the recent observation of the global lambda polarization tells that the fastest the fluid vorticity in the world emerges in heavy ion collision. So this fact strongly suggests that it is necessary to investigate the property of the rotating QCD matter, as the organizer selected this section. So in the analysis of the finite-sized system, probably the most important concept is finiteness of the system, as I used for my title, and as Kenji repeatedly told before talk. So for the most of the quantum system, we implicitly consider the large system, infinitely large system. More precisely, first we can we calculate some physical quantity. After that, we can take the thermodynamic limit. So in usual case, this procedure does not bring something troublesome, anything troublesome. But this is not the case in the rotating system. Okay, let us consider the rotating cylinder with angular velocity omega and with radius capital R. Then on the edge velocity B edge is given by omega times R. From the causality constraint, this quantity should be speed of light, namely the smaller than 1. Then you can find R capital R is upper bounded by 1 over omega. So as long as you consider the finite rotational velocity, then R should be finite. So if you consider the finiteness of the system, then there is a crucial influence for infrared physics. For example, if you take into account the finiteness of the system, then for its structure, the matter and the anomalous transport by the massless fermion are strongly affected. Okay, let us start from the just rotating system with the finite-sized cylinder. So let us start from the Dirac equation. So in order to introduce the rotational effect, in the quantum field theory, we can choose a rotating coordinate, or more generally, the fermion in the general coordinate system. Then in general coordinate system, the Dirac equation is given by this form. And if you consider the rotating system along z direction, and then you can choose the metric tensor like this, and you can choose corresponding the proper Vierbein. And we know that this gamma mu corresponds to the gamma mu is a connection to keep the local Lorentz covariance. And then you can explicitly write down the Dirac equation like this. So what you find from this equation is the first thing is that you have the rotational energy shift, which is proportional to omega. And then you can readily expect that distribution function, Fermi distribution function is given by this form f epsilon. And here also you can find that omega times L plus 1/2. L plus 1/2 is the quantum number of the total angular momentum. And here L is the eigenvalue of the Z component of the angular momentum. Then you can find, you can notice that this energy shift emerges as if it is an effective chemical potential. So in that sense, you can say that rotational effect is very similar to the finite density effect. So up to this point, we don't consider the finiteness of the system. So if you, when you introduce the proper boundary condition at R on the edge of the cylinder, then the transverse momentum P path is discretized, while the PZ is the momentum along the cylinder direction is continuous. Okay, we discussed the momentum discretization of the transverse direction. So before going to our case, it is very instructive to consider the simple quantum mechanics model, mechanics problem. So we have the bosonic particle inside the well with a length of capital L. Then if you put the Dirichlet boundary condition, the wave function is given by sine form, sine p times x, and the p is the momentum. And of course, the p is discretized like this, and which means so the p is given by the integer time, roughly speaking, integer over L, the system size L. And this has a lower bound for n equal 1, which means the lower bound is pi over L. So the momentum has the infrared gap. So similarly, we can discuss the momentum discretization for fermion in the cylinder. But in generally, the Dirichlet boundary condition is not directly applicable to the fermion because in general, the fermion has the fermion field is a 4-component spinor. So if you have the same component, if all of the 4 components are same function, then you can put the Dirichlet boundary condition. But in general, you cannot use a Dirichlet boundary condition. So instead of Dirichlet boundary condition, we can impose the different boundary condition. So now we employ the boundary condition in terms of the current along the radial direction, which means we impose that the radial current vanishes at R equal capital R. Okay, then you can get the discretized momentum. The P-pub is given by xi over capital R. And here xi denotes the case root of the Bessel function JL. So because the wave function is given by Bessel function JL. So this K, this level K corresponds to the above N, which means that even in this case, P-pub has an infrared gap. So minimum is Xi L1 for fixed L. So then we can draw the dispersion relation for the fixed L. And the different color represents the different level K. So blue one is the lowest, and the second one is yellow, and blah, blah, blah. And now we are considering the massless case for simplicity. So as I said, there is an infrared gap psi L1 over R for fixed L. Then there is then we need to recall the distribution function given by this form f epsilon. And further, for simplicity, let us consider zero temperature case. And you can rewrite the distribution function as this form. So this expression tells that there are two cases. The first one is the rotational energy shift, or we can say effective chemical potential. If effective chemical potential is larger than the gap, it means the distribution should be 1 at zero temperature, which means the rotational effect becomes visible. Another case is opposite, which means that the rotational energy shift is smaller than the infrared gap. In that case, you get distribution, vanishing distribution function contribution. So in this case, completely similar to the silver blaze problem. So then the problem is which is true. So actually, from the property of the Bessel function, you can prove that this inequality. So Xi is always greater than the 1 L plus 1/2. On the other hand, we need to keep the causality, which tells 1 over R should be greater than omega. So from these two inequality, we can get this relation. So which means that the latter case is true. Therefore, from this this simple analysis, we can show that there is no effect at zero temperature, which is coming from the causality constraint. This is one of the main results of this talk. But so far, we are focusing on the zero temperature case and without chemical potential. So if you have finite temperature or finite chemical potential, the situation is changing. So the rotational energy shift plays a role, effectively plays a role of the Fermi surface shift. And if you put finite chemical potential, of course, the mu also shifts the Fermi surface. And then you can get this situation. So which means you have, you can see the rotational effect, or the rotational effect becomes visible. Also, if you have the finite temperature, then there is a thermal excitation. Even also in this case, you can get the visible rotational effect. So this is one of the reasons why the chiral vortical effect is this form. So this is the current for wide fermion, which is discovered by the Blanking in this paper. So this means that chemical potential and temperature support the rotational effect. This is a good demonstration. So far, we discussed the general property of the thermodynamics in rotating frame. So now we analyzed the NGL model to discuss the chiral symmetry breaking in rotating system. So now we use this Lagrangian, and more, the precisely speaking, if you put some boundary condition, there is an inhomogeneity along the radial direction. So the dynamical mass from this NGL model should be in the space dependent. So for simplicity now, we used a local density approximation like this, and then you can solve the gap equation for each coordinate, small r. There are two plots for the dynamical mass as a function of radial coordinate r. So as I said, at zero temperature, there is no rotational effect. So we can see okay, so we don't write the explicit value for the omega here. And we choose the two different radial size, capital R. And if you put the cutoff scale lambda equals to 1 jeb, then this capital R corresponds to the size of the nuclei. And you can see that around the center, except for the vicinity of the boundary, you can see the flat plateau structure. But if you go to cross the boundary, then there is the boundary effect. Now, of course, in this region, the local density approximation is broken down, but qualitative feature can be seen from this plot. Okay, and also you can plot the finite temperature result, and you can see that if you increase the angular momentum, if you increase the angular velocity omega, the chiral condensate decreases, which is very similar to the finite density effect. And now we can evaluate the slope of the blue line here, which is a plot for omega r equals 0.3. In this case, this ratio is 0.2 or phi. So which means the blue one, this region is very varied even if you use the local density approximation. And I mentioned that there are similar work to plot the chiral condensate like this. And the first work to plot this, the result is Zhang and Liao, and the maximum and the Gongyo makes a similar plot here. Okay, this is a result for the rotating case. And also there are another interesting situation. So far we have no magnetic field, but if you put the magnetic field along the rotating direction, then dispersion here is drastically changed because of the Landau quantization. So in strong magnetic field, you have zero mode like this, and then automatically the rotational effect becomes visible. And this situation can be understood in the following way. So without magnetic field, the wave function is widely located in the cylinder. But if you put the strong magnetic field, then the wave function is localized, strongly localized, which size is 1 over square root EB. So which means localization leads to the bound localization enable us to ignore the boundary effect or the causality constraint. And then we can take a visible rotational effect. This is another understanding way. So there are two examples. Exhibits interplay between the rotation and the magnetic field. The first one is the density induced by rotation and magnetic field. So as I said, the rotational effect is very similar to the density effect. So but at the temperature, there is no density due to the boundary condition. But if you put some magnetic field, rotational effect becomes visible even at zero temperature. So which means that we can expect rotation yields the genuine density. So indeed, we can check from the very easy calculation from this Lagrangian with magnetic field and the rotation. And then you get the density proportional to B and omega, which is the same as Kenji showed in the previous talk. So this is one example. And second example is a chiral symmetry breaking under the magnetic field and finite angular velocity omega. So now I'm using the NGL model with a gauge field A and the connection gamma. And now for simplicity, I'm ignoring the inhomogeneity along the z along the radial direction, and then you can solve the gap equation to get dynamical mass m. And this axis represents the scale of angular velocity omega, and this corresponds to the magnetic field. So this plot shows there are two structures. The first one is this one. So you can see the slightly increasing the dynamical mass if you increase magnetic field for small omega. So this is nothing about the magnetic catalysis. And the second one is very special. So if you increase magnetic field, contrary to the first one, you can see the decreasing dynamical mass. So this is an inverse effect of the first one. This is very similar to the inverse magnetic catalysis or magnetic inhibition in finite density system. So as you know, the rotational effect is very similar to the density effect. So this is a good demonstration of the this similarity, and we named in this paper. So we named this structure the rotational magnetic inhibition. Okay, let us summarize my talk. The first part, I discussed the boundary effect against the rotational effect. So we need, in order to make the visible rotational effect, we need the temperature or density or magnetic field or some other source. These sources are necessary to get the visible rotational effect. And second, we get the novel chiral phase structure under the magnetic field and the rotation, and we name the magnetic inhibition. And so far, there are many works to discuss the chiral structure under the rotation, but I'd like to stress that this is the first demonstration of the rotational effect on the chiral phase transition. After that, Jin Feng and Maxim and other people checked without magnetic field chiral restoration happens at the finite temperature and so on. And there are other interesting situation. And the first one is without magnetic field, the rotation leads the neutral pion superfluid under the in a finite density system. And also recently someone discussed, including me, with Shugan, the charged pion condensate could be happen or not in the rotating magnetized system. Okay, maybe we need to stop the talk. Yes, thank you very much for attention.
Yeah, very interesting talk. Thank you very much, Kazuya. So we can pick up several questions. Yes. Yeah, Petrov, yeah, please go ahead.
Let me ask you the following. If we take, for example, the heavy ion collision, and as everything depends, then maybe one of the most characteristic is omega, the angular velocity, but angular velocity also is defined, to my mind, by the collision energy. And what's your feeling, impression that if we will increase energy from several GeV and collision energy, I mean, from several GeV to the highest LHC energies, several TeV, 13 TeV, etc. What will be the general effect on the effects you have discussed?
So it is well known that if you increase the collision energy, then the two nuclei, the throughs without interaction. Or in other words, so you cannot get the strong vorticity.
So everything disappears.
Yeah, I guess so. Or of course, if you have this small or tiny vorticity, then the phase structure is not affected.
So there is some maximum energy at which it is still makes sense to discuss all these effects.
So what do you mean?
You say that with the growth of energy, these effects they become less and less visible.
Yeah, I think so.
So there
I
is
think.
should exist some effective energy, maximum energy, at which it is still makes sense to discuss all this. And after this energy, if it's higher, everything disappears, and okay, other things may be interesting more.
So maximum energy does not lead to the rotational effect.
Okay. So you cannot you cannot say about that. For example,
I don't.
one TV still all these effects are observable or not.
I don't think there is a rotational effect in that case.
Okay. Okay. Thank you. Thank you.
Yeah. Thank you.
Okay. So maybe we should move to the next speaker. Let's thank Kazuya again for the nice talk.